Orthogonality is another subject that comes up very widely in numerical computing. Here we're going to talk about it in the context of the normal equations, but it's much broader. So again, here we have our our linear least squares problem. And I want you to recall a definition from linear algebra. The set of all possible vectors AX, okay, or all possible linear combinations of columns of A, is called the range of A, or many times this will be called the column space. It's the same thing. Okay, so that's a subspace of the Rm in this case, the output space of A. Okay, so what we're saying with the linear least squares problem is that we're finding the vector y in the range of A, right? Y is equal to A times X, that minimizes the difference between y and b in the 2 norm. And another way of seeing what does that is easy from a little cartoon. So imagine it's 2-dimensional, but the same picture would hold in multiple dimensions if we know how to draw it. So the range of A is some subspace, which means it has to be a straight line or a plane that goes through the origin. That's the set of all vectors AX. Okay, and then somewhere out in this space is the vector B, which we'd like to be able to reach, but in general we can't reach it. So if B were in the range of A, then of course we would have an actual solution to AX equals B. But it's pretty clear that among all vectors in this green space, the one that comes closest to B is the one that you get by dropping down a perpendicular. Okay, this would be the difference between B and Y. This vector that's in the space that's closest is Y, or A times X, at the linear least squares solution. So this perpendicular property, mathematically we call it orthogonality. That's the term that we use in higher dimensions. Sometimes you see the term normal used to mean perpendicular as well. All right. So the natural definition that follows from vector calculus is that two vectors in Rn are orthogonal if their inner product is equal to 0. Right? So you might remember from vector calc that the dot product of two vectors is equal to the length of each one times the cosine of the angle between them. So if that dot product is 0, we say the angle is 90 degrees. Now, very important property of orthogonality is that if two vectors are orthogonal, then the norm of u plus v squared is the sum of the squares of u and v in norm. And that's really basic algebra. So we use the definition of the 2 norm in terms of the inner product of a vector with itself. You write out what the inner product must be. If the two vectors are orthogonal, then these two inner products are both 0. And all that's left is norm of u squared plus the norm of v squared. So that's real simple to check. Of course, this is another statement of the first theorem you learned, probably, ever, which is the Pythagorean theorem, right? It says that if you have a right triangle, then you can compute the hypotenuse as the sum of squares of the other two sides. Well, why am I making a fuss about this? Well, we do know with norms that we have a triangle inequality in general for any norm. The norm of the sum is less than or equal to the sum of the norms. Now, if you have the 2 norm and you square both sides in the right way, you get equality. But if you don't have orthogonality, then this less than or equal to might really be much less than. And so a simple picture of that would be if u, let's say, is this vector, and v is a vector which is almost exactly anti-parallel to it. Right? Of course, we could exaggerate this drawing as much as we liked. Then u plus v would just be this little guy here. Much smaller in norm than either of the original two vectors. Well, that's a recipe for numerical cancellation. When we add two things and get a result which is much smaller than either one, we should expect to have cancellation of significant digits. It's just as true for vectors as it is for numbers. And so that's why we're really interested in orthogonality. Orthogonality prevents this situation. When you add vectors that are orthogonal or subtract them, then you're guaranteed not to encounter cancellation errors. And so now we have another reason for the name of the normal equations. So the normal equations state the following. So we can write them this way, okay, which means that if you take any vector z, which is in the range of A, okay, then it is orthogonal to the difference between b and ax. Remember, this is what we called b minus y, or it's also what we just call the residual r. So the normal equations are solved when you find that the residual of the problem is orthogonal to the range of A. Again, I'll go back up to the picture. Okay, the range of A is the green line. The residual is the normal to it. Okay, the best you can do is to make the residual orthogonal to the range, and that makes that distance as short as possible for the red vector. Okay. Now, if we want to go from two vectors in Rn to more vectors in Rn, let's say we have k vectors, well, we say that the vectors as a set are orthogonal if they are pairwise orthogonal. So the inner product between any two of them is 0 if you pick two different ones. Okay, so a simpler way of stating this is using matrices. So as usual, we'll stack those vectors that were given into columns of a matrix, capital Q. And then if you write out what the algebra tells you for Q transpose Q using the block form for the multiplication, you just find that Q transpose Q is a matrix of inner products between the vectors. That's more or less a definition of matrix products. And here the two matrices are transposes of each other. And so that means that the only ones that can be non-zero if the vectors are orthogonal, the only ones that can be non-zero are the ones that are on the diagonal. Okay, those are equal to norms. All the others would have to be 0 by orthogonality. So saying that the set of vectors is orthogonal is the same thing as saying that Q transpose Q is a diagonal matrix. Okay, so now we can take that a little bit further. So now we say that if Q transpose Q is not just diagonal, but a special diagonal matrix, the identity matrix. Okay, remember that Q is n by k, and Q transpose is k by n. So it's a k by k matrix. If you actually have the k by k identity matrix, then what we say is that the original vectors, Q1 to Qk, are called an orthonormal set of vectors. So normal means that they're normalized in this case. Right? Because that's telling us that Qi transpose Qi is equal to 1 for all I. In other words, the 2 norm of each of these vectors is also equal to 1, the square root of 1. Okay, so that's what we would say about the vectors. They're an orthonormal set of vectors. And then finally, if you have a set of n orthonormal vectors. In other words, if Q is square and its columns are orthonormal, then we say that the matrix itself is orthogonal. So this is terrible notation, terrible nomenclature, right? We're saying that vectors can be orthogonal, which says nothing about their lengths. If you do say something about the lengths of each vector, then they're orthonormal, and orthonormal vectors can make up an orthogonal matrix. I wish I could change it, but it wasn't up to me. Okay, so here we have an interesting thing. So we are saying that Q is a square matrix, and Q transpose Q is not 1, it's the identity, n by n. So in other words, the inverse of Q is the transpose of Q. So orthogonal matrices are the easiest ones in the world to find the inverses of. Just take the transpose. Okay, now we can prove a lot of things about orthogonal matrices. Here's 2 facts. So first of all, the product of 2 orthogonal matrices is also orthogonal. So let's suppose U and V are orthogonal matrices. Let Q equal UV, then Q transpose Q is UV transpose UV, which is V transpose U transpose times UV, which we can then reassociate using the fact that U is orthogonal, and then using the fact that V is orthogonal. That we've proven that Q transpose Q is the identity, so Q is orthogonal. That's relatively simple. Here's another one which I won't go into the proof of. One of the 2 statements is easy, the other one's a little harder. So we say that we have the fact that Q is an orthogonal matrix if and only if it leaves the 2 norm of all vectors unchanged. So if the 2 norm of Qx is equal to the 2 norm of x for all vectors x, that can happen only when Q is an orthogonal matrix and always when Q is an orthogonal matrix.